Hello folks, this is a follow-up to my previous video with regard to selecting the right scope for imaging. I ended up by saying the field of view was only one aspect of producing an image. The other is your camera, in particular how the camera sensor size and pixel size along with the telescope are factored into the equation to produce an image. This also leads to other concepts such as resolution, scale, oversampling, and undersampling, which I will also discuss. Why am I suddenly worried about all this? Well, I purchased a Celestron Edge HD8 a couple of months ago and wanted to ensure my new imaging train would work. I have no clue when the scope will arrive. It may be in China or sitting on a cargo ship waiting to dock in LA. So I also watched another video recently from James Lamb, and I'm going down the same rabbit hole he went through, and I will quote him in this video. I am Kurt Zepp, and you're watching AstroQuest 1. Okay, let's jump right in and we'll talk about sensor size. So these are some various cameras I own. I own the ASI1600. I own the ASI1600, and I do not own this, but I'll use it for test purposes. So I want to talk about the camera diagonal. That's how you talk about the sensor size. And for the ASI178, it's got an 8.9 millimeter sensor size. For the ASI1600, it's got a 22.2 millimeter sensor size diagonal. And the ASI 6200 has a whopping 43.2 millimeter sensor size. I'll talk about pixel size and resolution and all this other business later. So here goes. I'm going to use Astronomy tools in order to do this. This is a great program, and I highly recommend getting very familiar with it. Okay, so I'm opening up Astronomy tools here. What I'm going to use it for right now is a field of view calculator. I'll click on field of view, and I'm going to put it on imaging mode. Okay, so I'm going to show Pleiades. So you can actually have it do all sorts of whatever object you want to look at. So I'm going to keep my scope. I'm analyzing the different cameras, sensors. So let's go find my scope, and I'm going to keep the scope constant. And I'm just finding my Astrotech 115, and I believe it's right here. And it already has the focal length and the aperture and everything in here already. And let's go to the cameras. The first camera I'm going to go to is my ZWO 178. Now this had the smallest sensor. And here it is. Okay, it gives the resolution, the number of pixels, and the pixel size is already listed in here. I'm not going to put any bar low, so I'm just going to leave it alone, and I'm going to press add to view. And here it is, the Pleiades. Now you can see this sensor being so small, it was 8.9 millimeters. This wouldn't be a great camera to use trying to get all of the Pleiades. It's good if you wanted to get some fine detail, but for as far as getting the whole thing, this wouldn't be the thing to do. Let's go with the different camera. Let's go with the 1600, which is my standard camera. There it is. And we're going to press add to field of view for this one. And you can see it's got the pixels resolution and it's got the pixel size 3.8. Add this to the field of view, and look how much bigger field of view this is. This would be a good one to use. I can get it. It would frame it perfectly. Okay, and let's see what the ASI 6200 is. What that does. It had that huge sensor. 6200. Here it is. And look at the pixels in this one. And pixel size is about the same as the ASI 1600. Press field of view, and it's a much larger field of view. So similar to your changing your scopes, although you can do it with the cameras. And one thing I want to say about the file size that you're going to get from these cameras, the ASI 178, that's going to give you a small file size, relatively small file size that is. So this would be a good one to use for planetary work. and stuff like that, because you don't need a big wide field of view. You want to zero in on a nice planet, and you don't, since your field of view is very small, the planet anyways, it can download pictures real quick. The ASI1600, each one of those individual files is going to be about 4 times the size of the 178 file size. So you're going to be, you're not going to be able to download as quickly, and even when you're stacking programs, it's going to be a little bit more work for your computer to do some processing with. Now this 6200, beautiful camera, awesome, but the file size is 4 times the size as the 1600 file size. So if you want to do all your stacking and stuff like that with the 6200, if you get this camera, you better have the right computer too. You better have a supercomputer, because it's going to need a lot of speed. So just keep that in the back of your memory banks when you're buying these cameras. Okay, let's move on. Okay, before we get to resolution, let's talk about pixel size. Pixels are small, rectangular, or square photosites on a sensor that convert photons into electron signals. Now, on this little array that I have drawn here, this is my ASI 1600, and it's with 38 or 3.8 micrometer size pixels, and this is just a part of a 4x4 array. So the colored pixels on here are actually represent a star, this star right here, and I sort of colored it in as best I could to match what this star was, and it's zoomed in at 6,400 times. So this is what you would see if you zoomed in enough. You'd get down to the actual pixels. So each color represents the edge of your object that you're looking at. So pixel size seems simple enough. It's the size of the side of a pixel. Therefore, the smaller the pixel, the more resolution. Can it be that simple? Well, this is where the hard part comes in. One of the things is larger pixels have a better light gathering ability. And therefore, if they have a better light gathering ability, they're going to have more signal and less noise. So it's kind of a little tricky subject matter here. So going further into this resolution business, I'm going to turn to James Lamb, who made a recent video on this very subject in relation to autofocus methods. Now, I'm going to provide a link right here to his video, and I will also put the link in his description in my description section, and I highly recommend viewing it, as he goes into much more detail than I will. This portion will be a brief, watered-down version of what James went over. And first off, we're going to go over a few terms that you should know that are very important with this resolution business. First, there's the point spread function, and that you might be familiar with if you use PixInsight and do deconvolution. You might come across this term or other parts in PixInsight. Basically, that's the star. And this is an idealized star diagram, a point spread function or star intensity. You might see this in astrophotography tool that uses this in their focusing routine, or you might actually see this in PhD too. It's the graph, it's the star intensity graph. So what the point spread function is basically the star. So you've got your center of your star, and it's the distance from the center of the star, how far out it goes. Now, there's another term you may have heard, and that's called the Airy disk. And the Airy disk is the theoretical extent of the star. And here I've got it represented in this red line here. And there's actually a pretty fancy formula that goes along with it. It's 2r, r being the radius, times the wavelength times the focal ratio of your telescope. Now, in this idealized diagram I have here, this portion becomes 2.44. And if you want further discussion on this, go see James Lamb's video. All right. Now, the other term I want to discuss is this full width half maximum. I never actually really conceptually understood it until recently, though I watched James's video. And basically, it's exactly what it says it is. If you've got your star intensity diagram here, well, it's the width of the star at half maximum, half the maximum intensity. So this is full intensity down here, and half of the intensity would be halfway up. So this is the star diameter halfway up. And again, it uses the same formula, 2r times the wavelength times the focal ratio. And if in this idealized diagram, that value comes out to be 1.029 times the wavelength times the focal ratio. Okay, and I've got them defined right here. Okay, for the next part, how is this all relating to resolution and all this? Well, I'm going to get to that. First off, let's take a look at this diagram. And again, James Lamb did this thing, so I'm not the creator of these two diagrams. James actually did. I just did a different version than he did. But basically, this is your RGB colors. And it turns out blue has the shortest wavelength of light. So therefore, the blue signal is going to show the smallest diameter star, because remember, this airy disk is a function of wavelength. Green has a mid-range for focal or for wavelength, so therefore it would give the middle size star. And red, having the longest wavelength, you're going to have your largest stars with the red wavelength. So this is with my Astrotech 115. This is what the star would idealized look like. Now let's take a look at my Celestron Edge that I have yet to receive. What would the star look like here? And everything's gonna be the same in the fact that the blue is gonna be the smallest, green's gonna be middle, and red's gonna be the largest. However, the whole star itself is gonna be larger. That's because the airy disk is in addition to be a function of the wavelength, it's also a function of the focal ratio. My Astrotech 115 is an f7. This Celestron Edge is an f10. Okay, let's move along. So here's the resolution formulas. Now, these resolution formulas are actually based on no atmosphere. So atmospheric disturbance is 0. So here's a familiar looking resolution formula. I've seen this countless times. It's your pixel size divided by the focal length of your telescope, and they give this magic 206.265 value. And if you do the math, you get your resolution. And in my case, I'm getting 0.97 arc seconds. Well, first off, where the heck does this number come from? A larger version of this formula, again from James Lamb, this 206 is actually the conversion from radians. This value is in radians, and you want to convert it to arc seconds. So there are 180 degrees in pi radians. So that converts it to degrees. And then there are 3,600 arc seconds in 1 degree, and that's how it converts it to arc seconds. Now, if you did this part right here, it would give you 206,265. But basically, over here, the focal ratio is in millimeters. Here, we just converted it to micrometers. So, and there are 1,000 micrometers in 1 millimeter. So if you did this along with it and divide it by 1,000, that's where they get the 206 value from. So this is your maximum resolution based on my setup or your setup if you plug your own values in. You're not going to get any more resolution out of your system than this. So there's another theoretical resolution that's based on your FWHM, and that's Dawes limit. There's actually another one called Rayleigh's limit too, which I will not go over. But this one is Dawes limit. Basically, it's the same formula up here, only rather than putting your pixel size, you put the FWHM value in here. And so that would be 1.029, and you would multiply whatever wavelength you want to do it. In this case, a green, for example, that's what I used right here. So the green wavelength is 550 nanometers or 0.550 micrometers. Multiply it by 1.029, and my focal ratio is 7, and that's where I get 1.01 arc seconds. Now, this Dawes limit and this optimal sensor resolution, these values are pretty close to each other, which is good. This means I have a good match for my telescope and camera in this case. One other thing I wanted to say about this here is this is your sensor resolution based on the pixel size. You can't do anything with this number. This is your maximum resolution that you can ever get with your system. This Dawes limit, as well as that Rayleigh's limit that I did not talk about, those numbers are based on no atmospheric dispersion and perfect seeing conditions. Well, if you throw that in there, these numbers are going to go way up, but your sensor resolution will not go up. That stays the same. Okay, let's move on. Here's some different examples, including my yet to be received Edge 8. So the first one I want to show you is my Orion ST80, and that's an f5 telescope. And if I did the calculation on that, the FWHM value, converted it to micrometers, that came out to be 2.82 micrometers. And my pixel size on my sensor is 3.8. So that star would be smaller than the pixel. If you had that type of system, you'd be undersampled. That's what undersampling means, right? And how did I get this value right here? I just plugged it into that FWHM formula. So 1.029 wavelength, green light, times the focal ratio, and that's where I got that value. Next, here's my Astrotech 115, and the FWHM value for that came out to be 3.96 micrometers, and the pixel size is 3.8. So that's really close. That's what you want. You want your pixel size to be the exact same size as your star or your resolution, and that's considered optimally sampled. All right, and then my yet to be received Edge, which is the whole reason for getting involved in this whole thing. That came out to be 5.66 micrometers, and my pixel size is 3.8, so that's going to be oversampled. Okay, so what can we say about all these numbers? Well, they're not too far off. They're somewhat close. So your camera is probably going to be okay. There are some things you can do if you really are worried, and I'm going to show you that in a minute. But if you want more information about this, once again, I would highly recommend watching James Lamb's video. Okay, well, I think that's all I wanted to say about this business. Now let's go back to astronomy tools, and we'll go take a look at some of the setups that I described here, and I'll show you some things you can do with your camera when you're imaging to get the optimal resolution for your system. Okay, we're back with using astronomy tools. In this case, we're going to use one of the calculators here. So let's do this CCD suitability calculator. And before we go into using it, they give a little description of what's going on here. And they talk about FWHM over here. And they mention another equation, the Nyquist equation, and how you formula and how you can use that in order to calculate the best resolution. Also, they talk about on their calculator, they use the Nyquist equation. I don't know if I'm saying that correctly, but it's best I can do. Your typical seeing that you're going to have is somewhere between 2 and 4 arc seconds. And they say the optimal range of resolution that you should get or you should hope for your system is somewhere between 0.67 arc seconds and 2 arc seconds. So if you're in that range, you're doing pretty well. All right, well, let's go take a look at their calculator and see what they're talking about. So I'm going to go with my Astrotech first, and then I'll go to the Celestron Edge. So the Astrotech 115 EDT, and I'll use my ZWO ASI1600 if I can find it. I just had it. There it is. All right. And I'm not going to use a reducer or anything. I'm just going to leave everything the way it is, and let's see where we're at. And as I suspected, it is perfect. Look at that, right in the green zone. And according to this, See, the resolution is 0.97, which we already calculated before. Okay, so now I know that system is good, and that was a fluke. I didn't know that I was going to have such a good system when I purchased this system. I did not do any of this. It just happened to be. It was pure luck. But now let's take a look at my new scope that I have yet to really see yet. So it's the Edge 8, and we're going to try it. There we go. Blah blah blah. 2,000 focal meters. No Barlow. No nothing. And we see that the resolution is 0.39 per pixel, arc seconds per pixel. And that says the ideal pixel size is 0.67 to 2. This combination will lead to slight oversampling. So because I'm slightly oversampled, I've got to have very careful guiding. Okay, they say it's okay to do this, but it would be better. I better have a good system going here. Now, what can I do to rectify this? Well, what you can do is actually bind it. Let's see if I do binding, which this camera does. I'm going to bind it 2x2 or bin it. I don't know, bin, bind, whatever it is, whatever it's called. And now look at that, 0.77. So I'm in the good zone, and it falls really, really well. And so I might, if I'm using my ASI1600, I'd probably do better to bin it to 2x2. That means you're taking, rather than each pixel as a separate unit, you're going to bin it so you're doubling the size of your pixel, or actually you're quadrupling it because there'd be 4 pixels to 1. You could bin it 3 times, and let's see what that does. So binning it 3 times, I'd still be in the green zone. So perhaps I should do that. I don't know. When I get this scope, I plan to do some tests, and I'm going to try to test these very things out. So we'll see if that does anything. Now, another thing that I'm doing, or have done, or did, or planned for, I actually got another camera that I'm going to devote to this telescope, at least to start off with, and that is the ASI294 color camera. Now that has a larger pixel array already. That one's 294. Here it is, right here. Now this pixel size is 4.63, and it already started off better than the 1600. The 1600 is 0.39. This is 0.47, so I'm looking good with this. And let's see if I bin it to 2x2. Look, I'm in the green zone and I'm 0.94. This is perfect. Now, another thing is I plan to use this edge with not a Barlow, but a focal reducer. I purchased the Celestron 0.7 focal reducer, and let's see what the focal reducer does. Look at that. Without the reducer, it was, so none, it's 0.47. I put that 0.7 focal reducer on here, and the pixel size is suddenly 0.67. So there's another thing you can do as well. Use a focal reducer that can put you in the green zone. And let me see if I bin this with a 2x2, and I'm still looking pretty good. Actually, I might keep it at binned at 1x1. But again, I'm going to test all this out once I get it, whenever that will be. Okay, well, I hope this helped. As I said, this is a powerful little program, this Astronomy Tools. Look at all these calculators it has on here. There's a filter size function on here, because sometimes they have 1 1/4 inch or 31 millimeter filters, but they also have the 2-inch filters, so you can find out which kind of filter size is best for your thing. Your binocular, your CCD calculators, if you're going to purchase a CCD. So all these calculators are at your disposal for free on this Astronomy Tools. So let's go take a look at my final thoughts on this whole thing. Well, folks, some final thoughts. Sensor size can affect the field of view. The larger the sensor size, the larger the field of view. Physical resolution based on pixel size is the maximum resolution your system can have. It is the limit. Other resolution formulas like Dawes limit that are based on full width half maximum and such will increase as seeing conditions get worse. Your full width half maximum increases with the telescope focal ratio. Most camera sensors are designed for use with amateur telescopes, so oversampling and undersampling is not a major problem. There are some things you can do like binding to take care of that if you're concerned. Astronomy tools can be very helpful. And James Lamb really knows his stuff, and I'd like to thank him very much for dragging me down this rabbit hole with him. Anyways, that's all I have for you folks, and we'll see you next time.